Okay, guys, so today we're going to talk about evaluating limits algebraically. What that basically means is evaluating limits from their formula. And that's different from what we were doing last week with limits, because if you recall, last week, all the limit stuff we were doing involved graphs, right? I'd give you the graph of some function like this, and maybe I would ask you about what's happening at this point here. Maybe this is 2, and this is the graph of some function f of x, and maybe I could ask you, what's the limit as x approaches 2 of this function here, right? And hopefully you would say to yourself, well, this is a two-sided limit, right? There's no plus or minus here above the 2, and this thing only exists, if you recall from last week, this two-sided limit only exists if the left and right-hand limits agree, that is, if they're the same, and we can see here that they do not agree. They are not the same. As you approach 2 from the left, you're going to get this y value, whatever it is, and as you approach 2 from the right, you're going to get this y value, whatever that is. Those two y values are different, therefore this two-sided limit does not exist. So last time we saw how to analyze limits from their graphs, which this is an example of exactly the kind of thing we did last week. What we want to talk about this time is evaluating and analyzing limits without their graphs, instead by looking only at the formula for the function. So let's begin with the motivating example. So let's consider the function f of x equals, and instead of giving you the graph of this function, I'm going to give you the formula. X squared minus 9 over x minus 3. So let's have a look at this function. Suppose that we want to evaluate the limit as x approaches 3 of this function. Now, obviously, one way of doing this would be to graph this function, maybe with a computer, with Desmos or something, and then sort of look at what the graph is doing around 3. But suppose we don't have access to technology, right? Suppose that we just can't construct a graph of this thing, and we want to be able to evaluate this limit just from the formula. How can we do it? There's a pretty straightforward way of doing this, okay? And this is how we evaluate limits algebraically. So, how to evaluate limits algebraically. Okay, and what that means is without the graph, using the formula only. So how do you do it? So I'll talk about the general procedure, how do you do it, and then I'll come back to this example and we'll solve this question. It's a pretty simple process. There are really just kind of 2 steps, if you like. Step 1 is you just plug in the number. And by the number, I really mean this number right here. So if your limit is being taken as x goes to 3, then you should plug 3 into the function. All right? So whatever this number is here, you should just plug that into the function. And if you get a number, then that's the value of the limit. Okay, if you get a number, then that's the value of the limit. You're probably wondering, well, of course you're going to get a number. What else could you possibly get? It turns out there is something else you could get. You could get some kind of meaningless, undefined expression. Okay, so this is the second component. If you get a meaningless, or I suppose if you prefer an undefined expression, like, and I'll give you an example. What is an example of a meaningless expression? 0 over 0 is the one that you'll see over and over again. There are other meaningless expressions, but 0 over 0 is is kind of the most important example. So very often when you do this, when you just plug the number into the function, you'll get this weird expression, 0 over 0. And it turns out to have no meaning. It's not 1, it's not 0, it's not infinity. It really doesn't have any meaning. It is a meaningless expression. And so if when you plug in the number you get a meaningless or undefined expression like this, then here's what you do. Then you rewrite the function and you try again. Okay, and that's it. So that's a bit abstract, but let's see it in practice. So let's start by looking at the example we had a moment ago. All right, this function x squared minus 9 over x minus 3. So back to our example, I want to find the limit as x approaches 3 of the function x squared minus 9 over x minus 3. So I want to evaluate this limit algebraically without looking at the graph. So what does this procedure say? It says you just plug the number into the function. Whatever value you're taking the limit to, that's what you plug into the function. In this case, my x value is going to 3, so just plug this into the function and see what I get. So let's plug 3 into this function. So I have 3 squared minus 9 over 3 minus 3. Well, that's 0 over 0, isn't it? That is meaningless. That's a meaningless expression. It's not 1, it's not 0, it's what that signifies when you get 0 over 0 is that you have to rewrite the function somehow and try again. Okay? You have to rewrite your function, simplify it maybe, or rearrange it somehow, and then try plugging the number in again and see if you get something reasonable, see if you get a regular number. So let's go back to our function, the x squared minus 9 over x minus 3, and see if we can rewrite this somehow. Hopefully, you recognize that in the numerator, you can factor, right? X squared minus 9 is a difference of two squares. That can be factored. So we can rewrite that function as x plus 3 times x minus 3. That's how it factors. And then the denominator, I'm not going to change at all. And then what I notice is, oh, this x minus 3 here is going to cancel with that x minus 3 in the numerator. So I'll go ahead and cancel those. And I wind up with x plus 3. So what I've done is I've rewritten, really simplified, my function from this complicated expression to this much simpler expression. And now what I do, now that I've rewritten my function, I try again, right? I try plugging in my value into this new rewritten function. So if I plug 3 into this thing, I get 3 plus 3, which is 6, which is just a regular number. And as part 1 here says, if you plug in your limit value and you get a number, then that's the value of the limit. So this is the value of the limit right here, 6. Okay. So what did we just do? We had this limit as x goes to 3 of this function. The very first thing you try whenever you're trying to evaluate a limit algebraically without using the graph, the very first thing you try doing is you just try plugging this number in right here. You just plug it in and you see what you get. If you get something reasonable like 6 or 12 or 8 or negative 5 or something, then that's the value of the limit and you're done. But most of the time with these problems, you won't get a regular number. You'll get a meaningless expression like 0 over 0. And what that tells you is that you have to rewrite your expression somehow. Okay, factoring and canceling common factors is a very common thing that we have to do. But you have to rewrite your expression somehow, and then try plugging the number in again. And that's what we did. We rewrote our expression, we simplified it, and then we tried plugging in 3 a second time, and we got 6, which is, a proper number. So that's the value of the limit. Okay, so that's kind of all there is to it. So let's go ahead and do another couple of examples just to show you how this goes. So how about something like the limit as x approaches 6 of x plus 4 over x minus 4? Okay, let's have a look at that one. Well, the first thing that I should do when I'm trying to evaluate a limit like this algebraically using the formulas, I should just plug this number in. So let's see what I get. 6 plus 4 over 6 minus 4. That gives me 10 over 2, which is 5. Well, that's a perfectly well-defined number, right? That's just a number. So since that's just a regular defined number, that's the value of the limit. The answer is 5. It really is that easy sometimes. And, just so that we don't lose track of why we're doing this and what this really means, let's think for a moment, if you graph this function, okay, like on a computer or whatever, I'll sketch just like a small portion of it here. Maybe 6 is here, 5 is here, 7 is here, 8 is here. And then, this is maybe 1, 2, 3, 4, 5, 6. Okay, so here's 5. If you graphed this function, it looks something like this. Okay, something like this. All right, at least this portion. It sort of continues off the screen in this direction and off the screen in that direction. But one piece of the function looks like this. Okay, and what I want you to notice is that this point here, 6, 5, is on the graph. Okay, and so what this is telling you is that as you get close to 6, the value of the function gets close to 5. So as the x value approaches 6, so as you get really close to 6, like right here, the value of the function is getting very close to 5. So, all I'm saying here is that if you graphed this function and analyzed this limit graphically like we did last week, you would get the same result. You'd see that the graph is approaching 5 as the x value approaches 6, okay? But you don't have to do that, right? Okay, let's do one more example. Another sort of non-trivial one. Let's consider the limit as x approaches 2, x squared plus x minus 6 over x squared plus 3x minus 10. Well, we want to evaluate this limit algebraically without using any graph, so what's our first move? We just try plugging in the number, right? Sometimes we get a reasonable number the very first time you plug it in, and we don't even have to rewrite the function. That's what happened in this example. But let's see. Let's try plugging in 2, okay, into the function and see what happens. We're going to have 2 squared plus 2 minus 6 over 2 squared plus 3 times 2 minus 10. So what does this give us? Well, in the numerator, that's 4 plus 2 is 6, minus 6 is 0, okay. And then in the denominator, I have 4 plus 6 minus 10, that's also 0. Okay, 0 over 0, that's no good, right? That is a meaningless expression. That's not 0, it's not 1, it is undefined, it really doesn't mean anything. All it means is that we have to rewrite this function somehow and try again. So we have to simplify this thing, rewrite it somehow, and then try plugging in 2 again. And hopefully the second time around we get a reasonable number, like 12 or 2 or negative 3. So how can we rewrite this function? Well, you probably suspect that we should factor it and cancel common factors, and yeah, that's exactly what we should do. So the numerator here can be factored how? We need a pair of numbers that multiply to negative 6 and add up to 1. I think that would be x plus 3 times x minus 2 is how that numerator would factor. And then in the denominator, a pair of numbers that multiply to negative 10 add up to 3. That's going to be x plus 5 times x minus 2. So that's how the top and bottom of that expression factor, and as you notice, we have some common factors, right? The x plus 2 here cancels with the x plus 2 down below, which means that this expression simplifies to x plus 3 over x plus 5. Okay, so we have rewritten our function. And now we just try again, right? Now, instead of plugging 2 into this original version of the function, now we try plugging 2 into this version of the function. So try plugging in 2, and hopefully we get something reasonable this time. 2 plus 3 over 2 plus 5, that's 5 over 7. And yep, that's a perfectly reasonable number, right? So because that's a proper number, that's the value of the limit. Okay, the limit of this expression, it's 5/7. And what that's telling you is that as x gets very close to 2, okay, the value of the function gets very close to 5/7. Now, again, you don't have to look at the graph. That's the whole point of this, is to avoid looking at graphs. But if you wanted to confirm your answer, then you could look at the graph of this function, okay? You could look at the graph, and I'll just kind of sketch it here. You're not expected to know at this point how to construct this graph, right? You aren't expected to know why the graph looks like this, or what I'm about to draw. I just have a picture of the graph in front of me off screen. That's the only reason that I know what it looks like off the top of my head. But you could go on Desmos and graph this thing, or graph it on your calculator, and you'd see the same thing. So here's 1, here's 2, and this is 5, and then here's 1, and then this y value that we're interested in, 5/7, it's like maybe around here approximately. It's a little bit bigger than a half. Okay, so there's 5/7. And so what does the graph look like? It looks just something like this. At least this portion of it looks something like this. It is sort of interesting though, there's kind of a hole here. We'll talk about holes in a later lesson. So here's what the graph looks like, kind of a slow curve, and there's just a hole here in the graph. And first of all, let me address, why is there a hole there? Like, what's up with this little gap? Here's the thing. The original function, which this is a graph of, is not defined at 2, right? When we plugged 2 into this original function, we didn't get a value. We got an undefined, meaningless expression, 0/0. 2 is not in the domain of this function. This function is undefined at 2, basically because you get a 0 in the denominator when you plug in 2. So this function is undefined at 2. That's why there's this little gap here, right? We don't want to draw something there because that would be implying that the function has a value at 2 when we know it doesn't, right? So there's this little gap here just kind of indicating that the function is not defined at this point. But nevertheless, we can see, even though the function isn't defined at 2, the limit as x approaches 2 is defined. We can see that as x approaches 2, as you get close to 2, either from the left or from the right, the value of the function is getting very close to 5/7. So you can just confirm on Desmos that this limit we obtained algebraically is in fact the same thing as you would get if you did it graphically. Okay, it turns out that evaluating limits algebraically is much more important than being able to do it graphically. The graphical perspective is nice because it gives you a good picture of the meaning of the limit, like what does it actually mean. But in terms of computing limits, actually computing them algebraically is really the way to go. So that's just about it. I just want to say one more. In general, you're going to follow this procedure, right? You're going to plug whatever this number is here. You're going to start by plugging that number into the function. And sometimes you'll get a perfectly ordinary number, like we did here, 5, and that's the value of the limit, and you're done. But most of the time, most of the problems that we give you won't be that easy, right? That would be too easy if we made that happen a lot. Most of the time, you're going to have to rewrite this expression somehow, simplify it, do something with it, and then try again. Now, I keep saying rewrite the expression or simplify it, but you could rightfully ask me, what do you mean, simplify it, right? I've only shown you one trick. Okay, the trick that I used in this example was factoring and canceling common factors. That's also the trick that I used on this previous problem here that we did earlier, right? I factored and then I canceled common factors. That is very often the thing that you have to do. However, it's not the only thing. Like, there are a few other tricks, okay, that you're going to have to occasionally use to rewrite the function. Factoring and canceling common factors is one of the most common, but there are others, okay? One example that you will see in the worksheet is that, and I kind of give you guidance in the worksheet, but I give you this example. This is number 6 from the worksheet. I ask you to evaluate limit as x approaches 0 of 4 plus x quantity squared minus 16 over x. If you plug 0 into this thing, like if you plug this number into here, you get 0 over 0, which means you have to rewrite this expression somehow. It doesn't really look like something you could factor. Okay, so factoring is probably not the thing you want to do here. But you can FOIL, or if you don't like that word, multiply out, right? This 4 plus x quantity squared can be multiplied out, and you can collect like terms and so on, and whatever that gives us, it's going to be a rewritten version of the function. So let's try that. That's 4 squared is 16, plus that's going to give you 8x plus x squared. So these three terms here are what you get if you multiply this out and collect like terms. Okay, and then I've still got that minus 16 as well. Okay, all over x. Now at first this kind of looks bad until you recognize that this 16 is going to cancel with that 16. Okay, and that's going to give you limit as x approaches 0, 8x plus x squared over x. And now if you try plugging in 0, you still get 0 over 0, right? If you plug in 0 again here, you still get 0 over 0, which means you have to do something more. Okay, there's still something else you have to do. The thing you have to do is you have to factor and cancel common factors. The numerator can be factored. There's a common factor of x, which can be removed. So that's x times quantity 8 plus x over x. These two guys cancel. That's kind of a sloppy cancellation. Sorry, I got a bit excited. And then there's just 8 plus x left over, right? Now if I replace the x with 0, I get something sensible, right? Now if I replace the x with 0, I just get plain old 8. That's a proper number, right? That's an actual number, meaning that that's the value of the limit, okay? So what I'm getting at here is factoring and canceling common factors is one trick that you'll often use. Multiplying out and collecting like terms is something else that you might have to do. And there are a couple of other things that you'll sort of see on the worksheet, but I guide you through them. Okay, for example, there's complex fractions, right? If you see a complex fraction, you'll have to simplify it, right? But just be aware, okay? Like, look at the worksheet. There's a few bullet points, right, about the kinds of things that you might need to do to rewrite functions, okay? But I hope this is helpful. This is really exciting stuff because it's really the beginnings of calculus, right? In a way, this is kind of what everything you've done in math has been leading up towards. So it's a very exciting time. Okay, hope you all are doing well.